All right, hello everyone, and welcome to my channel. This is an educational channel. We look at some great theories of everything, try to do deep dives, and go into the details of revolutionary theories, esoteric and obscure theories from people who spent their whole life working on something, never really got any credit or compensated, and you've probably never heard of them, but if you did, you would appreciate their work. So today is our 416th video that we've done on the reciprocal system of theory from Dewey B. Larson. In 1959, Mr. Larson put out his two fundamental postulates, just two sentences about how the universe operates. The first postulate is the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. And the second postulate is that the universe conforms to the relations of ordinary commutative mathematics. Its primary magnitudes are absolute, and its geometry is Euclidean. And he took those 2 postulates through a process of deduction, like an if this then that kind of procedure, he arrived at his theoretical universe, what a universe would look like if his postulates were correct. And then in the remaining 30 years of his life, he wrote many books where he attempted to compare his theoretical universe with the empirical or actual universe that the scientists had measured in their laboratories and compiled in their tables. And so one of the books that he wrote in 1987 is called Basic Properties of Matter. This is the second volume of his 3-volume Structure of the Physical Universe, second edition. The first volume is called Nothing But Motion, which we went over about 6 months ago. And that's primarily on atomic physics. And then we didn't do the whole book, but 3/4 of it or so. And then Basic Properties of Matter on chemistry, and then Universe of Motion on astronomy. And so this book, Basic Properties of Matter, looks at Larson's derived equations for the basic properties of matter, and then, how he solves his equations or plugs in his equations to all of the elements and compounds, or many of them, and then compares his theoretical data with the actual data, and then tries to explain any discrepancies that might occur, or also explain similarities that occur. We had just gotten started with chapter 2 of his book that's called Inter-Atomic Distances. In the first chapter, he went over that was called solid cohesion, the basic kind of dynamics of how these things happen. And then in the second chapter, he's going to calculate the interatomic distances for the elements and compare them to the tables. Now, let me just try to quickly at least explain his first postulate. His second postulate we will set aside. There is some dispute about it from some of his followers, and in any event, most of it is just it's just saying that you have to accept math and geometry in order to get into this theory. I think Larson says it's something that scientists have to agree to in order to become scientists. Now, Larson proposes Euclidean geometry, and some of his followers reject that and think that there's a more inclusive kind of geometry. They call it projective geometry, that does the trick better, and that is more applicable. And I actually agree that they're correct, but this isn't really the time to go over that. And the first postulate is where most of the work gets done. And that has to do with that the universe is not made out of matter, it's not made out of energy, but it is made, or it's not made out of force, one of the fundamental forces. It is, in fact, made out of motion. And motion is the relationship between space and time. And this sets up a fundamental reciprocal relationship between space and time. Motion is basically a fraction with time or space as the numerator and space or time as the denominator. But space or time can come in multiple dimensions, and they can come in either order. So there are many, many permutations of space and time. And those are all our scientific quantities. These are all different kinds of motion. Matter is a kind of motion. Energy is a kind of motion. Speed, obviously, is a kind of motion. Acceleration is a kind of motion. Pressure is a kind of motion. Electric charge is a kind of motion. And they all are relationships between space and time. Space and time both have their three-dimensional aspects, which Larson calls coordinate space and coordinate time. This is the three-dimensional stationary frame. You could also call it the spatial reference system and the temporal reference system. And then when Larson is referring to the concept of motion, he's referring to a more generalized and less localized motion that he calls scalar motion. Normally we think of motion as a vector. It's got a direction, but scalar motion has no direction or just in or out. You can envision it as a balloon with dots on it. As you blow up the balloon, all of the dots are moving away from one another, but in no specific direction. And Larson calls that the progression. It's not that one dot is moving away from another dot. Each dot is moving away from each other dot. And if you suck in that balloon, then all of the dots will be moving toward each other, but again, in no specific direction. And that is analogous to what Larson calls gravitation. We get deluded into the fact that we think that gravitation relies upon a force field, that one big body is attracting a smaller body coming toward it. This does not come from scalar motion. The scalar motion has no direction, no field. It's just every dot is moving toward every other dot, just like on the surface of a contracting balloon. But if we arbitrarily decide that one of those dots is motionless, then when we start to evaluate the motions of other dots, then we can, it looks exactly as if there is a force field between the stationary dot and another dot that a reference dot. So the field, the gravitational field, Larson calls it an as-if force, or the force of gravitation, is actually a product of the reference point, the reference system, and not as a result of the scalar motion itself. So that is kind of why the scientists, the astronomers have noticed that all of the distant galaxies are moving away from each other. But instead of seeing that as a scalar motion outward, they've seen that as a big bang, that everything used to be at an original center point, and they're all moving outward from the center point. That is a way that you can interpret it, but you can also interpret it as the same as dots on the surface of an expanding balloon. Now, also, you have, again, you got this three-dimensional. So you have coordinate space and coordinate time, 3 dimensions of time in a still frame, 3 dimensions of space in a still frame, and then you have clock space and clock time, scalar motion in time, where everything is moving away from each other, and scalar motion in space, where everything is moving away from each other. And then you also have the discrete unit postulate. Both time, space, and motion are quantized. That means you have to have a full unit before you have anything. So you have to have a full unit of space and a full unit of time before you have space or time. And if you have exactly 1 unit of space and 1 unit of time, you have the speed of light, which Larson calls unit speed. 1/1 = 1. So this speed of light is the background speed of the universe. The universe is always and everywhere moving outward at the speed of light in all directions. This is the motion upon which the universe is built. And Larson calls that the progression of the natural reference system. And so if you have an empty universe with nothing in it, you still have motion outward at the speed of light in all directions. You have to be able to conceive of a motion without anything moving, because motion precedes the thing that is moving. And in fact, motion is the thing that is moving. Or really, the thing that is moving is motion. And this sets up, this discrete unit postulate basically sets up 3 boundaries in the universe. First, you have the unit speed boundary, this outward motion at the speed of light in all directions. That means that half of the universe is actually moving faster than that, and half is moving slower. Larson calls this the cosmic sector and the material sector. They are identical to each other, except that they have the roles of space and time reversed. So in the material sector, which is really the only sector that legacy science knows about, because Einstein says that the speed of light is the maximum speed of the universe, where Larson says the speed of light is the midpoint of the universe. In the material sector, you have 3 dimensions of space, coordinate space in a still frame, and you have clock time. The clock is always progressing, the flow of time. It's always getting farther and farther apart. And then once you cross that speed of light boundary and you move into the cosmic sector, then you have relations based on coordinate time, 3 dimensions of time in a still frame, and clock space. Space is always getting farther and farther and farther apart, the flow of space, just like on an expanding balloon. And so they're the same, other than the order, other than the roles of space and time. But then within both the cosmic and the material sector, there is a subregion. In the material sector, there's a subregion called the time region. And this is the region that occupies interactions that occupy less than 1 unit of space. If you don't have a full unit of space, then you don't have space. So if you don't have space, then you only have time, because the universe is made out of motion, which is made out of space and time. So it has to be one or the other or both. So if it's not space, it has to be time. So Larson calls this the time region. When you cross that border, that unit distance border, and move into the time region, the rules invert again. And the progression of the natural reference system is now moving inward towards 0, and the gravitation is moving outward, again, toward unit distance. Same is true in the cosmic sector, except that would be inside 1 unit of time. We have what is called the space region. And in the space region, cosmic gravitation is moving outward in time, toward unit time, and the progression is moving inward in time toward zero. Okay, now we're going to go, there's a million other things to say about that, but let's try to at least get some read here. And we're going to go back one paragraph from where we left off and then move on here in chapter 2 on interatomic distances. The interatomic distance is basically, when you're talking about the time region and the space region, those are the regions where atomic and molecular interactions are taking place. This is like the microscopic world. And within the time region, an equilibrium is established between the progression and gravitation. Where those two things are equal, you get an equilibrium. And so at that place, the two interacting particles are neither being carried further apart, that they would be under gravitational control, or moving closer together, that they would be under the control of the progression. And so that is what's called the interatomic distance equilibrium, where there is really no motion, because the motions are balanced. And so that's really what he's looking for. But in that case, the progression of the natural reference system is constant, but gravitation is variable. So you have to find the place where the gravitation equals the progression. And so that's what Larson's constructing his equations for. Okay. The first thing that needs to be emphasized as we begin our analysis of the factors that determine the interatomic distance is that we are not dealing with the sizes of atoms. What we are undertaking to do is to evaluate the distance between the equilibrium positions that the atoms occupy under specified conditions. In Chapter 1, we examined the general nature of the atomic equilibrium. In this and the preceding and the following chapter, we will see how the various factors involved in the relations between the rotations of the apparently or as if interacting atoms affect the point of equilibrium. And we will arrive at values of the interatomic distances under static conditions. Okay, that will be chapters 2 and 3, this chapter and the next. And then in chapters 5 and 6, we will develop the quantitative relations that will enable us to determine just what changes take place in those equilibrium distances when external forces in the form of pressure and temperature are applied. So we're looking here at what he calls static conditions under standard temperature and pressure conditions. And then later on, we will see how this interatomic distance is affected by temperature and pressure. As we have seen in the preceding volume, all atoms and aggregates of matter are subject to two opposing forces of a general nature, gravitation and the progression of the natural reference system. These are the primary forces, or motions, that determine the course of physical events. Outside the gravitational limits of the largest aggregates, the outward motion due to the progression of the natural reference system exceeds the inward motion of gravitation. And these aggregates, the major galaxies, move outward from each other at speeds increasing with distance. Okay, now, right now he's talking about the galaxies. So this is in the outside region, in the material sector, but not in the time region. Okay, these are two different dynamics. In the material sector, there is a place where the force of gravitation and the force of the progression are equal. but it is not an equilibrium because it is not a balanced. He calls that the gravitational limit. That is the astronomical limit. That more or less, if you're within that limit, then if you're a body within that limit, say the gravitation, every major heavenly body has a gravitational limit. If you are within that limit, then you tend to gravitate toward that big heavenly body, like the sun. The sun's gravitational limit is something like 3.61 light years. If you are within 3.61 light years of the sun, there's an equation for it. But for the sun, it happens to be 3.61 light years or so. And if you're within that gravitational limit, you will tend to move toward the sun. If you are outside of that gravitational limit, you will tend to move away from the sun. And in fact, there is a further gravitational limit at which you will, he calls it the second gravitational limit. Beyond that point, you will move outward at the speed of light. So there's kind of a zone there where you're moving outward from the sun, because gravitation has been nullified or neutralized at the first gravitational limit. It has been neutralized. At the second gravitational limit, it has been nullified or made negligible. And but within the time region, when you're dealing with atomic interactions, this equilibrium that is established is stable, a stable equilibrium, unlike this gravitational limit, which is an unstable equilibrium. If you tend to move toward the sun, then it tends to make you move further toward the sun. And if you move away from the sun outside the gravitational limit, it makes you move away from the sun. But within the time region, if you get closer than the interatomic distance equilibrium, then there's a force that kind of like a rubber band that kind of tends to move you back toward that equilibrium. Whether you get too close or too far away, this force brings you back to that equilibrium. So there's a difference whether you're dealing with something inside the time region or outside. That's what he's getting at here. So outside the gravitational limits of the largest aggregates, the outward motion due to the progression of the natural reference system exceeds the inward motion of gravitation. And these aggregates, the major galaxies, move outward from each other at speeds increasing with distance. Inside the gravitational limits, the gravitational motion is greater, and all atoms and aggregates move inward. Ultimately, if nothing intervenes, the inward motion carries each atom within one unit distance of another, and the directional reversal that takes place at the unit boundary then results in the establishment of an equilibrium between the motions of the two atoms. So if you, as whatever particle you are, whatever body you are, if you eventually get attracted to the sun, you will eventually move in toward the sun until you are within 1 unit of space, and then there's a reversal that takes place, and you will establish an equilibrium. There was something I was going to say about that. Well, it's just that the directions reverse, and you are carried toward this, toward really an atom. This is atom by atom that this equilibrium is established. between the motions of the two atoms. The interatomic distance is the distance between the atomic centers in this equilibrium condition. It is not, as currently assumed, an indication of the sizes of the atoms. The current theory, which regards the interatomic distance as a measure of the size, is, in many respects, quite similar to the electronic bond theory of molecular structure. Like the electronic theory, it is based on an erroneous assumption, in this case, the assumption that the atoms are in contact in the solid state. And like the electronic theory, it fits only a relatively small number of substances in its simple form, so that it is necessary to call upon a profusion of supplementary and subsidiary hypotheses to explain the deviations of the observed distances from what are presumed to be the primary values. As the textbooks point out, even in the metals, which are the simplest structures from the standpoint of the theory, there are many difficult problems, including the awkward fact that the presumed size is variable, depending upon the nature of the crystal structure. Some further aspects of this situation will be considered in the next chapter. The resemblance between the two erroneous theories is not confined to the lack of adequate foundations and to the nature of the difficulties that they encounter. It also extends to the resolution of these difficulties, as the same principles that were derived from the postulates of the reciprocal system to account for the formation of molecules of chemical compounds, when applied in a somewhat different way, are the general considerations that govern the magnitude of the interatomic distance in both elements and compounds. Indeed, all aggregates of electronegative elements are molecular in their composition rather than atomic, as the molecular requirement that the negative electric displacement of each atom of an element must be counterbalanced by an equivalent positive displacement in order to arrive at a stable equilibrium in space applies with equal force to a combination with a like atom. As we saw in our examination of the structural situation, electropositive elements are not subject to this restriction. But in many cases, the molecular or balanced orientation type of structure takes precedence over the electropositive structure by reason of collateral factors that affect the relative probability. Because of this fact, that the distances follow the structural pattern, various ways of orienting the atomic rotations that were discussed in Chapter 18 of Nothing But Motion, with a few modifications due to the special conditions that exist in the elemental aggregates, determine the manner in which the atoms of an element are able to combine with each other and the effective values of the specific rotations in these combinations. In the electropositive elements, the specific rotations are based, in the first instance, on the rotational displacements as listed in Chapter 10 of Nothing But Motion. Where the interatomic orientation is the normal positive arrangement, the displacements as listed are translated directly into specific rotations by addition of the initial unit and reduction of the incremental values where the rotation extends to vibration 2. Except for the elements of group 2A, which, as already noted, are subject to some special considerations because of their low magnetic displacements, the elements of division 1 all follow the regular electropositive pattern of specific rotations. The only irregularities are in the electric rotations of the second and third elements of each group, where the point of transition to vibration 2 varies between groups. The interatomic distances in this division are listed in Table 2. Okay, now, if I were writing that whole paragraph, which was very long, would be in a footnote, because it's kind of a digression. You know, he was talking about the nuts and bolts of things, you know, talking about, you know, the size of the atoms, but then making the distinction between, you know, the outside equilibrium and the time region equilibrium. But then he digresses into this whole thing about electropositive and electronegative elements, and, you know, how he gets into the history of science and talking about the electronic theory of bonding and how it's a similar mistake. And it's important, but it's kind of just disrupting the whole flow of, you know, we struggled just to understand what he was talking about before, and then to just kind of get into a whole different subject, you know, not a whole different subject, but a whole different aspect of that subject, strikes me as somewhat of a diversion. And if you would have just put that in a footnote, you know, you could have gotten it, but you could have stayed with the tenor of what he was talking about before. Now, the electropositives are basically, you know, the I guess it's the left side of the periodic table, with positive valence. Okay, so the regular electropositive pattern is also applicable in Division 2. Division 2 are the electropositives with the valence of greater than 4. Actually, it doesn't actually look like this is another fairly long paragraph. I think we'll stop here and get into this next stuff later. So yeah, just try to hang in there. Sometimes Larson, you know, again, he's writing for a scientific audience, and so you can get lost, and then, you know, he can go into a cul-de-sac and you don't really know why, and he's kind of just distracting us from the main focus of what he's talking about. I know he needs to get into this, but it's just difficult for the reader to kind of hop from one subject to another so quickly without any type of transition. Okay, so thanks for tuning in today. Stay tuned tomorrow for the rest of this chapter.